In the final part of this lecture, we're going to look at automatic differentiation, which is where we take the last few steps to make the computer do all the work of not only performing gradient descent, computing the gradient, but also maintaining a record of the computation graph so that backpropagation can be executed automatically. To explain, this is what we've been doing so far. We've been drawing, as it were, on pen and paper, a computation graph, and based on that picture of the computation graph, we have been working out rules for the gradient updates. And this is how we want to change that picture. We want to define only definitions of particular operations, and everything else we want to do in the computer. This is an instance of automatic differentiation. And to be more precise, this is what we call reverse mode automatic differentiation, which is where you apply the chain rule and accumulate the gradients backward from the output node, as we've seen in the last video. This is very efficient if you have one output node or if you only have a few output nodes, because to compute the gradients with respect to these different output nodes, you need to do one backward pass per output node. So the number of output nodes is the limiting factor in how efficient you are, and by our assumptions, we only have one output node, so this is for us always a very efficient way to do it. If you have the opposite picture, so if you have very few inputs but lots of outputs, then it's more efficient to accumulate the chain rule in a forward way, starting at the input node and working forward through the computation graph. The plan for this last video consists of 3 steps. First, we're going to build our automatic differentiation system on the data structure of tensors. So we'll look a little bit closer at what tensors are exactly. Then we'll show what common strategies there are for building these computation graphs. And then we'll look at how to work out the backward function for a particular operation, which is the only thing we need to do by hand before we can let the computer do all the rest. So let's start with tensors. A tensor is basically a generalization of the idea of a scalar, a vector, or a matrix. So what we call a zero tensor is what you might call a scalar, which is an element that contains one numeric value that doesn't change. A vector generalizes this in one dimension. So a vector is like a list of numbers, which we call one tensor, because the value changes along one direction. And the shape of a vector is expressed as one number, which is the length of the vector, essentially the length of the vector in terms of how many numbers it contains. A matrix is a two-dimensional version of this. So what we call a two-tensor that contains numbers, and these numbers change along two directions, which means that when we express its shape, we can do so by two numbers. How many numbers there are along each of these two directions. A three-tensor doesn't have a special name, but it's basically a generalization of this idea to 3 dimensions. So we have a bag of numbers that changes along 3 particular dimensions, and if we want to describe its shape, we can do so in a 3-tuple of numbers. And so on, we go to higher dimensions. So 4-tensor is a little bit more difficult to draw, but the basic principles are repeated. So how do we use these tensors to represent common types of data that we see? Well, let's start with a very simple classification task. So here we have 2 biometric measurements, 2 features describing a person for each row in our data set, and then associated to that a target class to predict the gender of the person being measured. So a basic classification task like this is usually split into 2 tensors, where the feature matrix becomes a matrix of the number of examples by the number of features, and the associated labels that we want to predict, either the classes in the case of a classification task or the numbers in the case of a regression task, will be given as a vector of the length of the number of instances in the data. You can also concatenate these, but this is usually how data sets are prepared. A more exciting example is an image, which is very naturally, of course, thought of as a pixel grid. So the pixels together form a matrix. And if we have a color image, then for each pixel, we describe it with 3 color values. In the RGB color space, then these stand for how much red there is in the pixel, how much green there is in the pixel, and how much blue there is in the pixel. So all of this together, an image can be described as a 3-tensor, where the 3 dimensions are width, height, and the color channels. If we then have a data set of images, we can describe that as a 4-tensor. So we just add 1 dimension, and that dimension indexes all the instances in our data set. And here's a little code sample from Keras. If you load the famous CFAR10 dataset in Keras and you print its shape, then you can see that it is actually represented as a 4-tensor of images, where the first dimension is indexes the instances the second and third dimension index the width and the height, and the last dimension indexes the colors. Tensors in most platforms, most systems, like NumPy or PyTorch, are what you might call a leaky abstraction. You need to know a little bit about what happens under the hood in order to use them correctly, but not much. So let's look into that. By necessity, the values in a tensor are stored in memory as a single sequence. There is no such thing as innately two-dimensional or three-dimensional computer memory. So we need to take these values, store them as a single sequence of numbers, and then use code somehow to translate that to a two-dimensional layout of numbers. But under the hood, every tensor is represented as a sequence of numbers. And the standard way of doing this in both PyTorch and NumPy is what is called row major ordering, which means that this sequence that the tensor holds in memory scans first along the rows and then along the columns. And this holds for higher dimensional tensors as well. So the scanning order is the rightmost dimension first, and then the one to the left of it, and then the one to the left of that, and so on. Using this principle, there are a couple of operations on tensors that we can implement very cheaply. In fact, in constant time. One of them is a reshape operation. If we want to keep the data in memory the same, but just change the shape, we can do so. So for instance, we can freely take a 2x3 matrix like A here and turn it into a 3x2 matrix with the elements still in row major order by creating a second tensor which takes the data from the first, by creating a second tensor which takes the data from the first, refers to it, doesn't even copy it, refers to the data from the first tensor A, and simply uses a different shape. So that's called a reshape or a view operation, and they're surprisingly useful. And we can even do this with a shape that has a different dimension. Like in this case here, we simply take the matrix A and we flatten it into a vector of 6 elements. To get some intuition for why you might want to do this, imagine you're loading an image data set. So here, as before, you have a 4-dimensional data set with dimensions, instances, height, width, and the color channels. And imagine you want to normalize this data set so that for each data set, the maximum color of each color channel, the maximum value along each color channel is 1. So you want to divide for each color channel by the maximum value in the whole data set within that color channel. In order to do this, you basically want to take a maximum over the first 3 dimensions, but 3 individual maxima for each index in the color channel. So to do this, you can use a reshape to collapse the first 3 dimensions into 1 dimension. And that's what's done here in this third line, where we say images.reshape, and we reshape it into 2 dimensions, where the first dimension is just all these first 3 dimensions multiplied by each other. And because we multiply, we know that the elements in the number of elements in the resulting matrix will be the same. Then we take the maximum along this new dimension. So basically the result of this is one big matrix of horizontally all the pixels in our data set, and vertically the 3 color channels. So it's a large number by 3 is the size of our matrix. And then along this vertical dimension, we take the maximum. And then we divide this data set, this big matrix, by this maximum, and broadcasting takes care of this division, so that it becomes an element-wise multiplication. And then after we've done that, that's the normalization operation we were looking for. And after we've done that, we can reshape the data set back into its original shape, which is what we see in this last line here. Now, this is very nice because this reshape is a very cheap operation. It doesn't cost us anything. It's constant time. But we need to be a little bit careful with it. Basically, this collapsing operation, where we combine 2 dimensions or 3 dimensions into 1, and then uncollapse them again, reshape them into their original dimensions, we have to be sure that we only do this with dimensions that are next to each other, and when we uncollapse them, we keep them in the same order. For instance, if we do this, we reshape the dimensions of n and h together and w and c together, and then we reverse the reshape, but change the order. We're allowed to do this. PyTorch and NumPy will allow us to do this, will not complain. But the results won't make very much sense, because in this new image tensor, the C dimension, for instance, it has a size of 3, but what it contains is not necessarily the 3 colors of one particular pixel. Everything is shuffled together. So reshapes are very nice, but we have to be a little bit careful to use them correctly. Another operation that we can easily apply without any cost is a transpose. So again, we turn a 2x3 matrix into a 3x2 matrix, but in a different way. Note that the result here is a different matrix than we saw before. And the way we can implement this is again by referring to the original tensor, but whenever we get an element ij of the new matrix, we simply refer to element ji of the previous matrix. And that automatically gives us a transpose. And of course, the shape of the new tensor is the shape of the old tensor with the 2 dimensions reversed. So that gives us a transpose. This isn't quite how transposes are implemented in NumPy and PyTorch, but it's good enough to show us the idea that we can basically do this in a constant time operation by referring to data of the tensor we're transposing. Finally, slices, again, we can implement in constant time simply by referring to the data of the original tensor, and in this case, just shrinking the shape. And if the slice is a little further along in the matrix, then we might have to give it an offset. But in this case, we can just reduce the shape and index by the same I and j as we did before. Now, this shows us a potential problem with all these constant time operations, which is that eventually, after we do a few of them, the data as it's laid out in memory might not be the standard row major ordering for the new matrix that we've created. This is called a matrix that is not contiguous. And if we try to perform an operation for which a contiguous matrix is required, such as a view operation, then we will get a runtime error. Here's the particular runtime error that PyTorch would give us. The solution is very simple. In PyTorch, at least, we can simply call .contiguous on the matrix or on the tensor and get a copy of the matrix which is contiguous. The price we pay is that this requires a copy, so it's linear time rather than constant time. That's all I wanted to say about tensors. In short, these are very useful objects, and we can represent almost anything we want in them. So these are going to be the basic building blocks of our automatic differentiation system. We are going to build computation graphs, and the things that flow along the nodes of these computation graphs will be tensors. So let's see what we need to build such a computation graph. We need to be a little bit more precise than we have been before about computation graphs. So from now on, we will draw them using 2 different types of nodes. The operation nodes, which represent the functions, the computations being performed on the tensors, and the tensor nodes, which represent the tensors that form the inputs and outputs of the computations, of the operations. The graph is bipartite, so an operation node can only connect to a tensor node, and a tensor node can only connect to an operation node. Tensor nodes have either no inputs, in which case they are the inputs of the computation graph, or they have one input, which is the operation node that produced them. And operation nodes can have multiple inputs and multiple outputs. So using these principles, we can, for instance, draw our feed-forward network like this. Note that the weights are now tensor nodes. We've separated these from the edges because they represent tensors, and in fact, these are the tensors that we want to apply gradient descent over. So these are the tensors that we ultimately want to find the gradients for. And note, of course, that the last node of the computation graph is not the output of our neural network, but the loss, because we want to compute the derivative with respect to the loss. The assumptions are the same as they were in the previous 2 videos. We have one output in our computation graph, which is the loss node, which holds a scalar value. And all the gradients we're going to compute are gradients of L with respect to the tensors on the tensor nodes. These can be very simply implemented using object-oriented programming. So a tensor node is an object defined by 3 members. Its value, which is a tensor, its gradient, which is a tensor of the same shape, and its source, which is optionally the op node or operation node that produced it. An operation node, similarly, is very simple. It's an instance of a particular computation, so it has a list of inputs and a list of outputs, and it refers to the particular type of operation that was used to perform this computation or will be used to perform this computation. And this op we have to specify separately. We could also do it within the op node, but usually this is specified separately into static functions or class functions. So we define an operation by two functions, the forward function, which is basically the function that computes the computation that it represents, and the backward function, which computes the gradient that we're interested in. This does not compute the local derivative, which we saw earlier. It computes the gradient of the loss over the inputs. We are given the gradient of the loss over the outputs, and we compute the gradient of the loss over the inputs. So if we have a function fa of b, which we want to represent in an op, we need to implement these two functions, forward and backward. The forward function of f is the function that given a produces b, very straightforward. The backward function is a function that given b nabla produces a nabla. And remember here that b nabla is the derivative of the loss with respect to all the elements in b. We also, in both of these functions, are given a context object, which depending on your system might be a dictionary or a tuple. It's some kind of object in which we can store things. And in that object, in that context object, we can store anything we need. During the forward pass, we can store stuff which we need to refer to during the backward pass. And we'll see some examples of how that works later. But now, with all of this in place, we have op nodes, tensor nodes, and definitions of ops. We can build our computation graph, perform the forward computation, and then given that computation graph, we can start at the loss node, traverse the tree backwards, breadth first, call backward on each op node, and since we're traversing breadth first, we know that the gradients for the outputs have already been computed, so we can pass those to the backward function of each op node so that it produces the gradients for the inputs. And if we do the whole tree breadth first like this, we can set all the gradients of all the tensor nodes in the tree. And in fact, it's important that we don't just set the gradients of the tensor nodes, we add the gradients to any gradients that are already there, so that if we have this diamond shape in our computation graph, then the multivariate chain rule on that level is automatically computed because the gradients are automatically added together. So this is the basic principle of our automatic differentiation system, and all we need now is a method to build up a computation graph for a particular computation. And there are two ways to do this: lazy execution and eager execution. In lazy execution, we first define our computation graph, and then we get our data and we feed it through the computation graph. And in eager execution, we simply perform the computation and behind the scenes keep track of the computation graph for the moment when it's time to start the backpropagation. Let's look in detail first at how lazy execution works in a kind of pseudocode. So we start by creating some nodes, some tensor nodes. So we have A and B, both of them tensor nodes. And in memory, these are objects that contain a value and a gradient. Note that when we create the tensor nodes, we don't know the value yet and we don't know the gradient yet. So that you can imagine these as being set to null or to none. We then define a computation on top of these. Despite the fact that we don't have their values yet, we can say multiply them. And if we want to do this in a nice way, we can overload the multiplication operator so that if we multiply these types of objects, what our system actually does is it adds to the computation graph an op node for the multiplication, and then it adds on top of that a tensor node for C, which refers back to this op node as its source. So this is the shape of our computation, but we don't have any values yet, so we can't actually perform the computation. In order to do that, we need to tell the system that we're done, we finished. This is our computation graph. So we tell it we have now built a model. The inputs to this model are the tensor nodes A and B, and the output or the loss of the model is the tensor node C. Given this, the system can say, okay, the computation graph is finished. I'll compile it. I'll do any optimization I might like to do. And based on this computation graph, we can start training. To train it, we need some inputs. So we tell the model, your inputs are 1 for A and 2 for B. Please do a forward and a backward pass to compute the output and then compute the gradients for all the tensor nodes in the computation graph. So we set these values A and B into the computation graph. We do a forward pass, so we perform the actual computation. So we know that C becomes 2 because that's 1 times 2. And then we reach the end of the computation graph and we start the backward pass. So for each tensor node in this computation graph, we're going to compute the gradient. The gradient of C with itself, like any derivative of anything with itself, is 1. And then we start a breadth first walk through this tree. So we arrive at this op node for the multiplication. We ask it, given the derivative of your output, C, which we have, give us the derivatives for your input A and for your input B. And it tells us the derivative for A is 2 and the derivative for B is 1. So that's lazy execution. It was the default in TensorFlow 1.0 and it's still the default in Keras, a library that is built on top of TensorFlow. The basic idea is that you define your computation graph, you state explicitly this is what my model is, and then it's compiled and then the data is fed through. One of the benefits is that this is fast because there's an explicit moment where you say this is my model, so at that moment you can optimize your model, get rid of any inefficiencies. It also makes it easier to serialize your model, and this serialization makes it easier to communicate your model between computers, for instance, for parallel training. The drawback is that it's difficult to debug. If something goes wrong during the computation of your model, you will get a stack trace, and that stack trace will point to this training line in your code, not to the line where you made the mistake in defining your model. A second drawback is that the model needs to remain static during training. You cannot have a kind of model where you have a different computation for every forward-backward in your training loop. Some of these problems are solved by eager execution. So let's see what that looks like. We'll perform the same computation. So we start with 2 tensor nodes A and B. But this time note that as we define them, we immediately define also their values. So when we create them in memory, their values are already set. And now, when we multiply them to create a new tensor node C, we create both the computation graph and we execute the computation to immediately compute what the value of C should be. So to us, writing this code, this feels very much like running an ordinary computation in Python, because we take 2 objects holding a value and we simply multiply their values and we get another object holding a value. And in the background, almost without us noticing, the computation graph records all the steps that we took. And when the computation graph is finished, there's no need to compile the model. We can simply decide what our loss node is going to be. So this needs to be an output node, which is scalar valued. And on that node, we can call a backward function to start the backpropagation process. And whatever the computation graph is that we've defined so far below C, that is the computation graph we will walk backwards over. So again, the gradient of C with itself is always 1. We ask the multiplication op, given this gradient over your output C, what is the gradient over your input A? And it tells us that's 2. And what is the gradient over your input B? That's 1. And that gives us the gradients for all the nodes in our computation graph. That's called eager execution. It's the default in PyTorch, it's the default in TensorFlow 2.0, and it's an option in Keras, although given the way Keras is set up, it doesn't make that much sense there. And the basic idea is that we build the computation graph on the fly during the forward pass. This makes it easy to debug because, in contrast to lazy mode, when we make a mistake in our computation, the crash, the error happens at the moment we make that mistake. And if we put, for instance, a print statement somewhere in our computation, then the print statement is executed at the moment that part of our forward pass is executed. So the forward pass is as easy to debug as any other piece of Python code, and it's flexible. So from one forward pass to the next, the computation graph is built up again and again and again. So every time we do this, the computation graph can theoretically be different. It does make it a little bit more difficult to optimize because you never say, this is my model, this is what's going to be running the computation, and it can be a little bit more difficult to serialize. So we've seen what tensors are. and we've seen how to build computation graphs. Now the only thing we need to do is define operations. For every operation that we might want to compute, we need to define it by writing a forward function and a backward function. And we'll now look at some examples for how to do that. And we'll start with a very simple one, the summation operation, which we'll call plus. And specifically, we'll implement the case where we are given two matrices and we want to sum these two matrices. The forward pass is very easy to write because it's just a plus b, both in NumPy and in PyTorch. So the question is, what should the backward pass be? And what we'll do in all of these examples, we'll first draw a computation graph that uses this op. So in this case, we have two inputs, A and B matrices. They go into an op plus, an output S is returned. Something happens to that S from which a loss is produced. And we can think of all the rest of the computation graph as basically one single operation because we already have the gradient for S of the loss. So it doesn't really matter what happens in the rest of the computation graph after our op. We'll take the same tactic we took in the previous video, where we first look at the scalar element of the matrix that we're interested in, and then factorize once we've worked that out. So in this case, let's start with A. What we need to compute in the backward function is the derivative for A, so A nabla, and one element ij of nabla is simply the derivative of the loss with respect to that element aij. And applying the multivariate chain rule tells us that we can sum out the elements of S in this fashion. So we index over S by K and L because S is a matrix, and we apply the chain rule in this way. The factor on the left, as we've seen before, we know this is what we're given. S nabla is G output in the code on the left. So we don't need to work that out, we can just fill that in. And the factor on the right, that's what we need to work out. So we fill in the definition of SKL, which is simply element KL of the matrix that we get by adding A and B together. And to write that in scalar terms, we can say, well, that's simply the KLth element of A plus the KLth element of B. BKL here is a constant, so we can get rid of that. There's only one term in this whole sum that is non-zero, which is when K is equal to I and L is equal to J, so we can get rid of all of the other terms. And the derivative that we have to finish is just Aij over Aij, which is 1. So we are left with a very simple result that the derivative of the loss with respect to Aij is simply the derivative of the loss with respect to Sij. So vectorizing this is very simple. The derivative of A, so A nabla, is equal to S nabla, and the same derivation applies to B, so B is also equal to S nabla. So now the question, how do we implement this in a backward function? We are given S nabla, which is here called G output, gradient of the output, gradient for the output. So we can simply return that value that we are given, first for A and then the same for B. We have two outputs for the backward function because the forward function had two inputs. Now, since there are some subtleties in the definition of the backward functions, we'll look at 3 more examples. Start with the sigmoid. The sigmoid is an element-wise function. So we take as input a tensor of any shape, we apply a sequence of element-wise operations, and we return the result. So in order to work out what the backward function should be, we first draw a computation graph. Something goes in, let's say a 3 tensor. The sigmoid is applied, the result is y, another 3 tensor of the same shape, which is fed to the rest of the computation graph, and a loss comes out. So in scalar terms, what is the derivative for one of these elements of x? We're looking for element I, j, k. When we apply the chain rule, we note that the output is also a 3 tensor, so we need to sum over 3 different indices, a, b, and c, and the rest of the chain rule is familiar. So we need to work out this derivative yabc over xijk. We fill in the definition, which is simply the sigmoid function. We note that this sigmoid is constant with respect to xijk unless a equals I, b equals j, and c equals k. So we get rid of all the other terms. And now the derivative that we're looking for is simply the derivative of the sigmoid function, which we've seen before, which is the sigmoid times 1 minus the sigmoid. So to vectorize, we can simply apply a series, again, of element-wise multiplications. And what we note here for the first time is that in order to implement the backward function correctly, we need to remember a value that we had access to during the forward. So we can either remember the value of x and compute this function as it's stated here, but actually during the forward pass, we already computed the value of sigma x. So we can actually just remember sigma x. And for this, we use this context object, which in this case is a dictionary. Sometimes it's a set of tuples. It can be anything. The main thing is it's a mechanism for storing stuff during the forward pass, which you can then retrieve during the backward pass. And in this case, what we need to store is the sigma of x. So we store that in our dictionary. And then when we get to the backward pass, when our backward is called, the deep learning system, the backpropagation system, remembers this context object for us, gives it back to us, and we can simply retrieve from the context object sig x and apply the element-wise computation that we've just worked out. The next example is a row-wise sum. So we are given a matrix and we sum out the rows. What this shows us is what happens when an operation gets a tensor of one shape, one dimensionality, and returns a tensor of another dimensionality. In this case, we get a matrix and we return a vector. Again, we're interested in the derivative for a scalar element, so we apply the multivariate chain rule. Note that in this case, the output only has one dimension because it's a vector, so we only need to index over one dimension, which we do here using the variable k. We fill in the definition of yk, which is the sum over the kth row of x. We work out the sum, we eliminate any constant terms, and we're left with this, which is simply the derivative for yi. Now to vectorize this, note that we are interested in a matrix of derivatives, which is defined in terms of a vector. So we need to look at this a little bit carefully, and what we see is that this tells us that x nabla is basically a matrix consisting of the vector y nabla as its columns. So if we repeat the vector y nabla and concatenate it a bunch of times, then we end up with the matrix x nabla. And in notation, we can achieve this by taking the outer product of y nabla with a vector of 1s. And in code, what we would do is, at least in PyTorch, we would insert a singleton dimension, which is done by this non-keyword in the slicing syntax, and then expand one of the dimensions to a particular given value. Note that when we sum out the rows of x, we lose the information of the full two-dimensional shape of x, so we need to store how many columns x had. We store that in the context object, we retrieve it during the backward, and then we use that information to expand y nabla into x nabla. One more example, an expansion op, and this op starts with a scalar value and expands that into a matrix by simply repeating the scalar value for all the elements of the matrix. And in NumPy, this is done by the keyword full. So here's what that looks like in a computation graph. Note that in order to do this, we need to specify the size of the output matrix. So we have two arguments, the scalar x and the size of the output matrix, but we cannot reasonably expect a gradient over the size of the output matrix because this is a pair of integers. So even if we could compute a gradient over this, it wouldn't make any sense. So for that reason, we've drawn it as a dotted line. And we need to somehow communicate to the backpropagation system that there will not be a gradient over this part of the input, which we'll see later how to do that. But first, let's work out what our gradient is for x, which is done very simply by applying the multivariate chain rule. We have two dimensions in the output, so we sum over two dimensions with indices a and b. We fill in yab, which is simply x for every element of y. So this is our derivative. The gradient for x is simply the matrix representing the gradient for y summed up into one scalar value. Note if we compare this backward op with the last one, there's a very neat symmetry. If we expand something, then the gradient is a sum. And if we sum something, then the gradient is an expansion. Implementing this is relatively straightforward. We simply take the gy that we are given, we sum up the values and return those. And for the second argument, we return a value none, which communicates to the backend that there is no gradient over that particular edge in our computation graph. So those are the three main things that I wanted to discuss. A few more details. Most deep learning systems also include a functionality to define a module or a layer, which is a slightly more high-level concept built on top of the concepts that we've already discussed. So what we see here, for instance, is a PyTorch linear layer, which is an object that combines a number of parameters together with some computation in order to define a linear layer. So here we have a weight matrix W, a bias vector B, and the code that tells us how to multiply an input by the weight matrix and add those bias values. Now it's important to note that a linear layer has a forward function, which tells us how to do these computations, but it doesn't have a backward function because a backward function is specified implicitly because we use operations to perform this forward function. So when it comes to the backpropagation, it doesn't really matter whether we are applying these two operations manually or using a linear layer to do so. We can simply think of the linear layer as a kind of utility function that does this for us. Which brings us to the end. This is the ideal that we wanted to achieve. On pen and paper, all we have to do is define operations and work out their forward functions and their backward functions. We program those out, and given that, we can leave everything else to the computer. The computer can, for us, build a computation graph, and using that computation graph, perform a perfect backpropagation pass on tensor values, which is fully vectorized. So let's look back at the whole lecture, all 4 videos. We reviewed neural networks. We looked at backpropagation, which is an algorithm that helps us compute a gradient, which we can then use in gradient descent. The main principle is that we work out local gradients symbolically and global gradients numerically, and we work from back to front, applying the chain rule, accumulating these gradients. We looked at how to vectorize this into what we call tensor backpropagation, and used 2 important assumptions to be able to do so. We assume that there's a scalar loss, and we are always computing the gradient of the loss. And then finally, we looked at some methods for purely automatic differentiation, where the computer maintains the computation graph for us so that it can do backpropagation by walking backwards through this computation graph, breadth first. So that's all for this lecture. In the next lecture, we will look at convolutional neural networks.